also. All right, so today we're going to go through the calendar real quick to make sure that you know what to expect. So today is Friday that feels like a Monday, and so I'm just all confused. But today we are going to go over conservation of energy and make sure you understand it as best as I can hope for. Anything that you need beyond this, then we can supplement this weekend. We'll get there. We are going to quiz on Monday, okay? And on last Monday, the last time we were together, I went through what was going to be on that quiz, so I'm not going to take time to do that today. If you were not here or you do not remember, you can go back and watch that video, and that will tell you exactly what is going to be on the quiz, but it's going to be energy and conservation of energy is the, kind of the long and short of it. On Tuesday, the next day, we'll work on mousetrap cars. So I know that some people have worked on them already. There was at least one that got dropped off this morning that's beautiful and works and is awesome. So if you did that, fantastic. That's what I was hoping you might work on over those 3 days of cold, which is why I didn't send you other stuff. So if you were waiting for other stuff, I apologize for that. But we will work on mousetrap cars on Tuesday or review for the test, whichever is more honest for you. We will test mousetrap cars on Wednesday, and then I'm going to go ahead because we're kind of far behind and I don't want to, fall further and further behind. I'm going to plan that we will test over work power and energy on Thursday of next week, okay? So that comes up kind of fast, but I think we can do it. The one thing that I would recommend is that you pay attention to what we've been doing and don't just turn your brain off and say, oh, I don't need to do it because I'm going to build a mousetrap car. I would strongly, strongly recommend, because this unit has been kind of funny, that you spend a little time, like every day, right? A little time every day. You guys have heard this from teachers forever, right? A little time every day is going to make it much better than trying to cram it all in next Wednesday night, okay? So a good thing to think about for testing over work, power, and energy on Thursday. Today, after having done that, yay, we're going to go over some homework if you have questions. And then I've just got a bunch of conservation of energy practice. The more practice we do, the better we're going to feel, and the more confident we will be with this test. Sound good? Issues right now or requests, things that you want to make sure that we do today that are not on that list? Okay. So the first thing that I had on my list, it was actually on the list from the last time I saw you, was to go over homework. And I can't remember if I asked you about the homework, if you had any questions, but I wanted to make sure that I put that out there in case there were questions that you wanted to go over. The answers are up there. So I'm going to put that out there. Anybody is welcome to ask. So let me know if you have a question. I'm very happy to go through things. Otherwise, like I said, I've got plenty of things for fun as well. So any of those problems that you would like to go through, or anything else problem-wise that are things you want to go over? No? Okay. If you have not been spending time doing homework, friends, a friendly reminder that, again, that would be a good thing to be doing. This is what we've done so far this unit. So way back to work and power, okay? The test or the quiz that we take Monday, excuse me. The quiz that we took, the last one was on the 14th. That was a long time ago. So we've been working on this for like half a month. It's kind of weird. So kinetic and gravitational potential, thermal and elastic potential, conservation of energy, that's where we're at, okay? So that's the stuff that you want to go through. And if you have not done this homework, do it, okay? Do it. Let's go through some examples then, if there are no questions. All right. I've got a ranking task because, you've been sitting and not doing ranking tasks, I'm guessing, for the last few days of your existence. So let's take a look here. I don't think there's anything above that you need to see. Nope, it just says kinetic energy. Shown are blocks that slide down a frictionless incline. The masses all start from rest at the top of the incline. Okay. The question asks you, or the task asks you, to rank the kinetic energy of the sliding masses the instant that they hit or that they reach the bottom of the incline. Okay, so nothing is stopping them. No friction is happening. So rank their kinetic energy here, here, and there, etc. Question.
Can I get a whiteboard?
Absolutely, you may. In fact, I'll go get whiteboards for everybody. But you can come up and get one if you want right now, and then you'll have it first. You can have your first pick. All right, give this a shot. Think it through. If you want to talk to people, great. If you are like, wow, it's been a few days, I don't even remember what kinetic energy is, maybe get out your equation sheet. Would you like a whiteboard, Maya?
There's only one more marker.
Oh, I've stolen a couple up here. Do you want? No, you like your paper?
She won't.
Nope. Thank you for helping out. I appreciate it. They don't really maintain their shape there. That was impressive. Got some. I'm assuming you need a little more time. Is that true? Or are you guys ready? I'll give you another couple seconds. All right. So let's first start with some answers. Let's see if we can get there, and then we will make sure we can walk through it. So we've got some, why don't you put some answers up? I'll go ahead and write them down, and then we'll see where we're at. So I see, I'll fix it in just a second. Thank you. A, C, E, B, D, F, A, C, E. Did I miss one? F, A, C, E, B, D, F, A, C, E, B, D, B, A, C, F, D, E, B, A, C, F, D, E. Oh, D, E, D, E. Okay, so we got two distinctly different answers there. Yeah? Help me out. Hopefully one of them's right. I don't know because I don't remember the answer. How did you solve this problem? Mass times height. Mass times height. Why did you do mass times height? What's that? So they're what kind of potential energy? I want to do this right. Gravitational potential energy, okay, at the beginning. And if we were going to write this out as a real conservation of energy equation, we'd also have to add the kinetic energy at the beginning, right? But how much kinetic energy is there at the beginning, Leanne?
0.
Why? 0. I'm just going to write this here because the velocity is 0. Is that okay with everybody? I just want to make sure this is explicit so that you get it. Okay, so we're there so far. And then we're going to set that equal to the energy at the end. I'm assuming that's where you were going with this. Is that true? Maybe I'm trying to put words in your mouth. And if that's the case, then I apologize for that. Okay, so now what can I do? Why? Because it is moving. Well, it's moving when it's here. Does that mean the potential energy is 0?
It's at 0.
It's at the H equals 0, right? Yeah. So I'm going to say because H equals 0. That's an H. Can you tell? And so just to remind ourselves, I'm just going to put this up here so I don't forget, again, because it's been a few days. that gravitational potential energy is mgh, and kinetic energy is, you remember the expression for that one? 1/2 mv squared. And those are, again, both on your equation sheet. So you have those, but just to kind of get those in your head. So you have potential energy at the beginning has to equal the kinetic energy at the end. And so, why did you say m times h?
Because you would be the same for all of them.
Okay, so I am assuming you're talking about this one since you told me that this one was 0. You're talking about this one, the mgh? So mgh here is equal to the kinetic energy final, but you're saying the G is going to be the same for all. So this is that little advantage of having a ranking task where it's not actually saying, what is the kinetic energy, right? If you were asked to find the kinetic energy, then you would need to find the potential energy, which means you'd have to include the G. Is that okay? But they want you to, now what are you ranking down here? I guess I didn't even look. What are we ranking? The kinetic energy. And so you have to take a step here. So if you had something like this on a quiz, I don't know, or something like that, perhaps. If you just said, and I'm not saying you would, but I'm saying if a student had a question like this on a quiz and ranked them correctly, but then just said, and I'm not saying that theirs is right, I don't have any, we haven't gotten that far yet, but in the explain your reasoning just said G times H, or not, excuse me, M times H, I'd be like, so what? You have to take me through these steps because mgh equals the kinetic energy at the bottom because of conservation of energy. Without that, the whole thing that she's saying is out the window. Okay? All right. So, Leanne, you are suggesting, again, not trying to put words in your mouth, but trying to gather what you were saying. M times H, because G doesn't matter. The product of the mass times the height is going to be equivalent to the rank of the kinetic energies. Now, that was, which one were you? You were the FACE one? Okay. My BAC FDE people, what did you guys do? Did you do that? Or did you do something different? Well, it wasn't just, I mean, you were not the only person that had that written down. There were lots of people that had this written down.
I was looking at the height difference and thinking about potential energy being the same as kinetic energy at the end. And
Yeah.
in the last experience, mass turned it out. But
That's what I did.
I wasn't looking at like the difference in how in the last experience it's the same mass.
I feel
Oh.
like we made it more complicated than it was.
Okay. Now, I want you to hold on to that for a second, okay? Can you just like hold on to that nugget? Don't forget it.
I wrote that down too.
So you canceled out your masses too, just like.
And then I just looked at the height the entire time.
Yeah,
And
me
then I
too.
didn't pay attention to the mass at all.
Interesting. Okay. So I just want to write this down so that I've got this kind of for posterity and also for our friends that are not here today, or if you guys are watching this again over the weekend. So this, what you were the BAC FDE people, right?
Yeah.
So this was ranked based on height only, right?
Yeah.
This one was ranked on M times H. Okay, so the question here says kinetic energy. So does it make sense that we've got to have the M times the H in there? So then we're going to take 10 times 1, 10 times 1. So A and C have got to be the same, yeah? And they are, because they're the same height anyway. 5 times a half, 1 times 2, yeah?
Mm-hmm.
So for those of you that had the ranked based on H1, does this make sense to you now?
Yeah.
Does anybody want me to go through like the numbers of it? I'm happy to if you'd like. Are we okay?
Yeah.
Okay. All right. So I'm going to put a little circle around this as answering that question. Are we good? So now my next question, because I like to, reuse and recycle, we're going to do the same thing, same picture, same everything. Oh, go away there, thing. Except that instead of writing kinetic energy here, I'm going to write velocity. Rank the velocity of the sliding mass the instant they reach the bottom. Can you do that? Rank the velocity of the sliding mass. And by that I mean not just telling you how to do it, but let's figure it out. So I just copied and pasted this to another one so we could look at it again, except we're changing kinetic energy to velocity. They're the same pictures, right? How do you find the velocity? Or is there a quantity that's related that we can figure out to talk about velocity? I'm just trying to figure out how we can find velocity.
Go back to
All that work you did before. I'm going to rewrite it out here. So again, if you're stuck or you're not sure, you just want to get this in your brain. We're just going to remind ourselves that the gravitational potential energy at the beginning, this is what you wanted me to write. Is this right, Leanne? Is that statement okay with people? This statement is a statement of what? Where does that come from? Conservation of energy. This is just saying that the total energy at the beginning has to be the same as the total energy at the end. That's all it's saying. We asserted last time that we did this problem, or one like it, that the kinetic energy was 0 at the beginning and that the potential energy was 0 at the end, right? Potential energy is 0 at the end. We're assuming, or we're setting H equals 0 down here, right? Okay, so just to be very clear about that. So why does she want to do that? Where does this suggestion come from? It says rank the velocity. Is the velocity hidden inside here anywhere? Where is it waving its little hand? Where is it saying, I'm here, hello? In the kinetic energy, right? It's in the kinetic energy. It says 1/2 the mass times the final velocity squared has to be equal to m times g times h at the beginning. Are we okay? Now, we want to know velocity. Can we maybe write an equation for velocity here, or get so we can get velocity by itself? How would you do that? What do you want to do, Leanne? Say it loud. Cancel out the masses, right? Divide by mass on both sides or cancel them out. G times H equals 1/2 V squared. Now, we could do that extra algebra to solve this for V. You probably will need to on Monday. Okay, but does the G change? Does the 1/2 change? 1/2 is 1/2, right? The only thing that V depends on is what? The only thing that V depends on is what? H? So, yeah.
Yeah, that was the one that we're looking for.
Yeah.
That's why I wanted you to hold on to it. Absolutely. As H goes up, the velocity goes up. Okay? So if you were here on Friday, we did something a little bit more exciting than just straight ramps, but it was the same idea. It was the same idea. So I want to make sure that this is kind of still sticking in your brain. We looked at, where did that one go? Was it here? Yeah. You remember this little picture? And some of you are like, I didn't watch the video, so I don't remember it. But here it is. So Paul and Kathleen, same kind of deal, blocks on a ramp. Seems like we're, dismissing them or making them a little smaller than they need to be. But how are their velocities going to compare at the bottom? Help me out. How are their velocities going to compare at the bottom? What is velocity dependent on, you guys?
No.
Only what? The height. Only the height. So Paul and Kathleen are going to get there, and they're going to have the same velocity when they get to that point. If you leave the same height, you're going to have the same velocity at the end. Who has more kinetic energy at the bottom? Do they have the same kinetic energy at the bottom? You're making an assumption to say that they have the same kinetic energy at the bottom. You don't know their mass. So who's going to have a bigger kinetic energy at the bottom? We don't know who, right? Because it might be like Kathleen is like the mom and Paul is like the kid, right? We don't know who has a bigger mass, but you can tell me that the one with the bigger mass will have a bigger kinetic energy at the bottom. Okay? Let's write this down because I feel like we need to process this and understand this. Okay? So we're going to do a conservation of energy of an object on a ramp. Only kinetic energy and gravitational potential energy involved. Because if you start to put friction in there, then things get all messed up. I will not have a problem like that on a quiz, okay? But I will have a problem like this on the quiz, which is why I want to make sure that you understand it. Conservation of energy of an object on a ramp with only kinetic and potential energy involved, okay? Kinetic energy at the bottom depends on what? That was the first problem we just did. It depends on the potential energy at the top, which, if we say that gravity is going to be the same for all of them, because we assume that they're all at the same relative place on Earth, depends on the mass and the height. The velocity at the bottom depends on what? Only on the height. Only on the height. Okay? This is not something that I want you to memorize. I don't want you to read this 5 times before you go to bed every night between now and Monday. I don't feel like that's a good use of your physics time. But I want you to understand that there's a difference between quantifying the kinetic energy and quantifying the velocity, okay? Any ramp that has the same initial height will result in the same velocity at the bottom, okay? It can be a really, really big person and a really, really small person, a really, really big block and a really small block. Does not matter. Same height, same velocity, because the masses cancel out, okay? Does that kind of make sense? It's a little weird, but I want to make sure that you've seen it and you kind of understand it. We ready to move on? Right, and who's going to get there first? Does that depend on mass?
Bigger kinetic energy at the start.
Right, whoever transfers their kinetic energy first, yes. That's what's going to matter, absolutely. And does that depend on mass?
No.
It does not.
No.
It just is dictated by who goes down. Yeah, goes down first. All right. My favorite conservation of energy problems all involve roller coasters because they're fun. So here we go. Here's the situation. Assuming that the height of a hill in the figure is 40 meters. So that's this Y right here. So not all the way down to the bottom, but to the bottom of this hill. Okay. Assuming that the height is 40 meters and the roller coaster starts from rest at the top. So if you've ever ridden a roller coaster, this is like that spot where they hang. You know what I'm talking about? You're like, oh my gosh, you get really excited. Maya, do you like roller coasters? I was trying to gather based on, she's like, this sounds like a terrible thing to do on a day off, right? Like, no, I love this. It's so good, right? So starting from rest at the top, I would like you, now we're going to calculate, so we're going to do the math to find the speed of the roller coaster car, that should say at the bottom of the hill. That's part A. And then part B says, this is a little more interesting. At what height will it have half of that speed? Interesting. I'm going to give you a little while to work. Do you notice that there's something missing from all of this? What have they not told us about that roller coaster car? They haven't. Do you need to know the mass?
No.
You don't need to know the mass. That's great. Which is really reassuring for people that don't love roller coasters, like especially if you think about the loop ones. It doesn't matter how much mass you have, you'll still be able to do it. Okay, regardless of if you have just a bunch of little kids on it or a bunch of like really, really big people, does not matter. It's all the same. You'll go the same speed regardless. So there you go. Can't slow it down by getting your, I don't know. I was going to say Uncle Charlie, but I don't want to make any assumptions about your Uncle Charlie. You know what I'm saying? But like, you can't slow it down by getting big people to ride on it with you. All right, give this a try, you guys. Write it out. This is the kind of stuff I like. This is the kind of stuff that you might see in a few days on a quiz. Talk to each other. Figure it out. Draw a picture. First thing that I would write down, a conservation of energy statement. Just like we've done a couple of times already today. Yeah. So I write it out. Just so you don't get confused.
We choose the height for the one.
Exactly. Yep. So I will tell you that when you do this problem or one very similar to it on Monday, if you just start with numbers, you won't get full points. In fact, I want to make this clear because it's important to know. If you just start here, you will not get full points. Okay? You must start with a statement of conservation of energy.
explain mu again?
Can I explain what?
Mu again?
Sure, it's coefficient of friction.
Okay.
So it's how sticky or slippery two surfaces are when they're sliding against each other.
You said if we have to go to the bathroom, we can just go.
Go, yeah.
The dude kept saying it. I couldn't remember what it was.
I know it's so frustrating with this science. Is that you have to drop like everything you know about science and then just live with it.
Yes. It's all good science. It's all correct science. Yeah. I mean, the people that write it have PhDs, most of them. Yes. But
I'm just reading.
it's not reading comprehension. It's drawing conclusions. It's interpolating and extrapolating. There's good science skill in there, but it's not science content. That is true. And that is hard. But it's good in the sense that even if I've never taken biology, I can still do the biology, right? As long as I get over the fact that the names are weird and all that kind of stuff.
I did see a chemistry thing though.
Yeah,
There was a problem where you had to actually know how to.
Yeah. So on actual ACT science test, out of the 40 questions, there will only be one what they call background knowledge question where you actually have to know something. Yeah. So unlike the practice ones, that might not be true because they don't vet them in the same way. But yeah.
This is my lowest score.
Really?
Like every time
We can work on it. Seriously, like if you want to, let me know. Yeah.
I'm taking it next weekend, so it has to be
We can do it. Let me know. Yeah.
I mean, it's still like pretty high, like, I bring my score down.
Yeah. Yeah. There's good stuff, but it's not content, which is, like I said, in some ways is good because like I don't know any biology. So, yeah. But yeah, sometimes it's hard though. Sometimes it's surprising the things that people think are hard when like the writers don't think they're hard. It's funny. It's like, why did that not pass? We don't know. All right. Are you guys ready to kind of talk or not yet? One more minute? Do you need another minute? Are you sure? Okay. All right. Let me turn my recording back on.